Good afternoon from sunny Belgium. My name is David Vos. I'm the director of Vos Software, the makers of ModelRisk, and I'm giving you a 3/4 to 1 hour presentation on the topic of correlation. I'm going to start with an introduction into the meaning of correlation and why it's useful. I'd like you to take notice of the number codes that come across there in red, usually in brackets, and they start with M and then they have a number afterwards. If you want to read more about the topic that is being discussed in each slide, then you enter this information into the search field in the ModelRisk help file, and it will take you directly to the subject that you're interested in. So first of all, let's talk about terminology. There are 3 terms that are frequently mixed up, misunderstood. They are correlation, dependency, and regression. Let's start with correlation. If 2 or more variables go up and down together, or perhaps they go, when one goes up, the other one goes down in value, then we say that they are correlated. Correlation does not imply any reasoning. So we don't know why, perhaps why these 2 variables or more tend to go up or down together. We just want to recreate the observed pattern. And certainly when you are looking at data, you may find correlations, for example, between stock prices of 2 seemingly independent variables, independent stocks. And yet we see that they go up and down together. We don't know why, but we want to reproduce that type of behavior. Sometimes, however, we do know why. Perhaps there is a third factor that influences them both, but we're not interested in modeling that third factor and its relationship explicitly. We simply want to model the effect of that third factor, not relationship with the third factor. So that's correlation. It's simply that 2 variables, random variables, go up or down or behave in some way without specifying the reasoning or the direction of the relationship. Dependency is different. Dependency is the next level of sophistication, and it says that the value of one variable affects the value of another. For example, age affects height. If you think of children tend to be smaller and younger. Only up to a certain age there are no relationship between age and height after a certain age. Perhaps you can say that old people get a bit shorter. So height is dependent on the age, but not the reverse. Now, in a situation like that, we could model these 2 variables as correlated variables, but we could also model a dependency relationship, as we'll see later, and sometimes we want to do that, in which case we need to know the causal direction. Which variable is being affected by which other variable? In this case, of course, we have modeled the height as a function of the age. And that brings us to the third term, regression. Regression is a mathematical model that relates the dependency of one variable to another. And it could be several variables, all influencing another variable. And there are several types of regression. The linear regression, most people are familiar with. This is a sort of straight line relationship between the dependent variable and the independent variable. But there are others like logistic regression. Logistic regression attempts to explain why the probability of an event can go up or down, or is affected in some way by other variables. A Poisson regression models how the frequency of events in time, for example, fires or outbreaks or insurance claims, can be affected by other variables, like weather. Weibull regression talks about the lifetime of a device, how long a piece of equipment will work, which could be related to a number of variables like the temperature that the equipment is working in, or the level of dust in the environment, or how old it is even. So dependency and regression, they both assume that we know the causal link and the causal direction. Let's start off with a very simple type of correlation, And this is for a dichotomous variable. Dichotomous variables are ones that either take the value of 0 or 1, yes or no, etc. So in this little table, it's a 2 by 2 table, and we notice we've got on the vertical axis whether or not a person has cable TV, and on horizontal axis we see whether or not they have the internet on their phone, so a smartphone, and they have internet connection. And there are 27% of people have neither. 6% of people have internet on their phone, but they don't have cable TV, etc. So the matrix gives the probabilities of the 4 possible combinations. We notice that the probability that someone has cable TV is 38% plus 29%. It's the sum of these 2 different probabilities depending on whether or not they've got the internet on their phone. And similarly, probability that they don't have cable TV is the sum of the second row, which is equal to 33%, and the whole thing must add up to 100%, much the same way as within this matrix, 2 by 2 matrix, they must add up to 100%. You can also read the vertical columns, sum them to say that the probability that a person has the internet on their phone is 35%. This is pure correlation. We do not make any statement about which variable is influencing the other. So we don't say whether having the internet on your phone influences the chances that you're going to take cable TV or vice versa. In this simple example, it's very easy to model it. And here I've given the same matrix on the left-hand side and showing you how you can model this type of correlation. In the first variable here, first cell, I've got a Bernoulli distribution. A Bernoulli just returns a 0 or 1. In this case, it's a Bernoulli about whether or not a person has cable TV. And you can see that we use the probability of 67%, which is the probability that they have cable TV irrespective of whether they have the internet on the phone. So this will return a 1 whenever we're generating the scenario that a person has cable TV. And the second variable is connected to it. It simply says that if that value is 1, which means that they did have cable TV, then the probability we want to pick from this Bernoulli is equal to F7 over H7. That's the probability that they had internet on their phone, given that they have cable TV. Otherwise, we pick the other one with the probability that they have internet on their phone, given that they don't have cable TV. And that second probability is used when they have cable T variable is equal to a 0. Just to check, I can run a simulation on this, and with a little bit of logic using the sim mean function, if I run a simulation, I can reproduce these probabilities here, and you see that this is what has actually happened. So the simulation mean, when you've got a flag that's either 0 or 1, the mean is equal to the probability you will have a 1. And I'm reproducing those same statistics here. Okay, so that was our first very simple model. Life becomes a little bit more complicated when our variables are not dichotomous. We can't split up the world into yes or no, male, female, alive, dead, zeros or ones. When we can't do that, we'll have a variable that takes several values. Here, I've got 2 variables, the height and the weight. And you can see that to some degree they are correlated. These are actually real data. So this variable can take any value below, say, 60 kilos up to 80 kilos. What I want to be able to do is reproduce this pattern so that when the height is somewhere down in the low 60s, this is height is, yeah. I don't know which way around. I think the height and weight are the other way around. But so when one variable is down towards the low 60s, the other variable is down towards the low 140. And when one variable is high, the other variable is high. These are probably inches and pounds. So there are lots of examples where we have situations like that. We have two variables that are continuous and we want to represent that some sort of relationship between them. Height and weight, as I've just shown you. Disposable income and the frequency of visits to restaurants. Now, and the yield rate of corn and of wheat in fields. And you can see that some of these is not just pure correlation. We could actually say more. Height and weight. Well, your weight does not confer anything about your height, but you can, the other way around is true. Taller people tend to weigh more. In the second example, people with more disposable income tend to be able to afford to go to restaurants more often. Whereas here, the third example, there is no sort of dependency relationship that we could talk about. The yield rate of corn and of wheat, they're probably related to a third variable outside of our model, something to do with the weather, whether we have sunny summers and we have a decent amount of rain. So why do we correlate? Why is it important for us to do it? And why is it challenging to do? Well, correlating variables tends to increase the tails of the distribution. It's not a fixed rule, but in many of the types of problems that we deal with, certainly when we're doing with things like summing up costs, or we're dealing with times to complete a project, but there are many other variables. If we do not recognize the correlations between, say, distributions of costs, then certainly when we add up those costs, we will have underestimated the tails. The reason we do that is because we're underestimating the probability that you can have a high value for one variable and have the high value of another variable occur at the same time. If we underestimate the tails, then we underestimate the risk. And that rather negates the whole purpose of performing a risk analysis. Perhaps one thing worse than not performing a risk analysis is to do it very badly, because at least if you don't do a risk analysis, you don't believe that you've understood the risks well. If you do a risk analysis but do it badly, you can falsely believe that you have a good understanding of those risks. The problem is that correlation is difficult to identify. We quite often fail to consider the common causal factors. For example, two tasks in a project might be completed by the same team. And we might look at those tasks individually and not really consider that they would be correlated. But if that team is very inefficient or very well led, then we will have correlations between the time it takes to do each of those two tasks. On the other hand, sometimes if we see a correlation, we can convince ourselves of a often wrong reason why there is a relationship between them. That makes it much more difficult for us to have a consistent way of thinking about correlations and causal relationships. If you follow our newsletter, we gave some rather interesting examples of correlations and asked you to submit an answer about why you thought those correlations existed. We've had some pretty interesting answers, I must admit. Correlation patterns can also be quite complex, and they don't sometimes fit the standard models that we might imagine. And I'm going to give you some examples of that in a minute. And low levels of correlation are really very hard to spot. Certainly, from an experience point of view, it's very difficult to know that there are correlations from your past history. Even though we might believe that those correlations exist, we won't have, even if we collect the data, very often good information that tells us about the level of correlation. There are some fields where this is very different, where they're very data rich. Here is an example in these two scatter plots. Now, on the left-hand side, I've got the two variables plotted with their values. And it's quite kind of difficult to see whether or not there is much correlation. Certainly, we've got a concentration of values to the left, but that means that this first value variable here, most of its values are just between 0 and 2. But is there really a correlation structure? I'm not so sure. We have 276 points here. In fact, if we do a correlation statistic, we find there's a 26% correlation. And on the right-hand side, you can see that this is a correlation pattern where we've used the percentiles instead of the values themselves. So the 0 would represent the lowest value, 1 represents the highest value, 0.5 represents the value which 50% of the data were above and below. And you see perhaps some small level of correlation, perhaps a greater density of dots in this top right-hand corner and this bottom left-hand corner than there is in the bottom right and the top left. But it's not very convincing. Statistics allow us to see correlation where perhaps the human eye doesn't see it. How do we use correlation? Well, there is a Sklar's theorem, and you can go look that up on Wikipedia or something, that says that we can define or fit, if we've got data, distributions for variables independently of their correlation. So we just look at the data we have, or we make an estimate from subject matter experts about the range of values that a particular variable can take. And then separately, we can define the correlation structure. In this way, we have the ability to control how the distributions are sampled in a Monte Carlo simulation by separately defining the correlation structure. So here I have two variables, and they're just triangular distributions to make life easy. And you can see with the arrows that this is trying to show you how the correlation is working. What we're doing is sampling high values with high and low values with low. A method for estimating the level of correlation that is in common use is something called Spearman's rank coefficient, or rank order coefficient. And it takes this formula here where U and V are the ranks of the data you've got. And so if you saw the data in pairs and you had, say, 100 points, the second largest for one variable would get the value 2, and the 10th largest would get the value 10. And what it does here is it takes one value, one rank, minus the other for the same level of observation, takes the difference between them, squares it, adds them up, etc., where n is the number of data points you got. And I managed to mess this up, but that should say between -1 and +1. I apologize for that. So rho lies between -1 and +1. 0 means there's no correlation. And that's quite useful. It tells us, it enables us to identify whether there is correlation, often, not always I have to admit, but often. Certainly if there is a single direction of correlation, in other words, it follows that as values one variable gets bigger, the other one gets bigger all the time, or smaller, or whatever, but not where there is some sort of U-shaped relationship, then correlation will fail us. What it doesn't tell us is anything about the shape of the correlation. So to illustrate that, I've got 4 correlation patterns here. They're quite different shapes, but they all have the same rank order correlation of 0.9, 0.9 being a very high level of correlation. So with rank correlation, we can identify usually, not always, but we can usually identify where there are correlations if we have sufficient data, but it still doesn't tell us the type of pattern. In ModelRisk, we use copulas to simulate correlations between variables. And here I have 5 different examples of the 5 copulas that we use. First is a Clayton. The Clayton pinches in one of the corners. If it's a bivariate, then we can pinch in one of the 4 corners. We can rotate this graph. But the Clayton has more concentration of correlation at one end than it does at the other end. The Frank is kind of a sausage shape. It has even level of correlation all the way through 0 to 1 percentiles. The Gumbel has pinched correlation at both ends, unlike the Clayton, but it has more correlation at one end than the other. Then we have the Student, which has a slightly unusual correlation structure in that it can form a star shape. And then we have over here the normal correlation. This is the normal copula. It's the one that you'll find in most other risk analysis software products. So most other products only have this one correlation type. Now, there are many situations where fitting a correlation using statistics, which software can do, they only have this one type of correlation, they're going to very much underestimate the real risk. So if this was profitability of two stocks here, and this was how the real variables behaved, then you wouldn't get the appropriate level of risk about losses in both variables at the same time. There's a higher probability of losses in both variables that will be recognized in a Clayton copula than will be recognized in a normal copula. So to my mind, it's somewhat curious that we have risk analysis software that has many types of distributions. Most software will have at least 30 types of distribution, but only one type of correlation. As I mentioned before, in the bivariate case of correlating with ModelRisk, you can rotate using the direction parameter. It's an extra parameter in the bivariate case. You can rotate the essence of the correlation. So it can be correlated at minimum minimum, maximum minimum, maximum maximum, or minimum maximum, these four corners. So how is a copula implemented in a simulation model? It's implemented in exactly the same way, no matter what software you might use, but this is specifically how we do it in ModelRisk in terms of functions. So first of all, you have a copula function. This looks like a Clayton copula, and if the Clayton copula, that's a bivariate Clayton copula, takes two values, generates two values. So here we have two values, 0.65, 0.75, whichever, and here they are. The star represents where those two values have been generated. So a copula covers two cells in a spreadsheet. And with those two cells, it's able to generate these two values. When it's generated those two values, we pass them through distribution functions. In this case, I've got a log normal distribution and a normal distribution. We pass them through these distribution functions, which would normally generate random values for the normal and log normal, but we're using the extra parameter called the U parameter. You'll find that with any of the univariate distribution functions in ModelRisk, you will find an extra U parameter. So these are the parameters that define, for example, the normal distribution, the mean and standard deviation, and this is a third optional parameter. If you don't include it, then this normal distribution will be sampled without any reference to any other distribution. So the way the functions work is that they look at the cumulative distribution function for the log normals and normals. They read off this value here, which in this case is 0.65, and they say, what is the value of the variable that would have a 65% chance of being below? And similarly down here, of 75% chance of being below. And it reads off these numbers. Now, the reason it can do that is because a copula, if you were to take all these dots and plot them on the horizontal axis, it would be uniformly distributed between 0 and 1. There are equal probability of having a value between 0.9 and 1.0 as there is between 0.4 and 0.5. And that same can be said for the cumulative probabilities. There is an equal chance, by definition, that this random variable will take a value between its 0th and 10th percentile as between its 40th and 50th percentile, for example. So marrying these two ideas together, we can simulate from these two distributions in a correlated way. So you can imagine that when we get a value generated down here, we will get a very low value for one variable occurring at the same time as a very low value for the other variable. So to see this in practice, we just open this very small model. In here, you will see there are two cells, because of it's a bivariate copula, that are covered by this same function. The curly brackets represent that you have an array function in Excel, meaning it's not a function that just covers one cell, it covers multiple cells, in this case two, because we have two variables. And then over here, I have a normal distribution, we don't worry about the output for a second, but a normal distribution, 100, 10, as I mentioned before, and then B8, or cell B8 is referring to the copula. If I was to view function on that cell, you would see the slide that I showed you previously. You would see that we've got this random number between 0 and 1, which comes from the copula. In this case, it's 0.1029, etc. That is being fed into this function to read off the value from the cumulative percentile. So the value 87.35 has a cumulative probability of 10.29%. So using that U parameter, if I name these two as outputs, then I can actually run a simulation and see that they're going to reproduce a correlation pattern. I'll do that in 1 second. I'll just show you another way we could have done it. We could have used normal objects here. This is just a function that defines a random variable. It says that this is a normal 100, 10. This is a log normal 10, 3. And then we use a simulate function. Simulate says simulate from this random variable using this U value. You'll see that these two give exactly the same answer. Now let me just run a simulation. I'll start a simulation of 1,000 values. And here you will see that these two variables are correlated in this scatter plot. I can show you the correlation where I've got the values again plotted against each other, but also I can change the mode and show you the percentiles. And there you will see the replication of that now hopefully familiar Clayton copula pattern with a great deal of correlation at the bottom end and less correlation as we go towards the higher end of each variable. Okay, so we now understand how copulas are implemented in ModelRisk, but how do we fit them? How do we define the values? Well, the normal way of doing it is to do it through fitting. So we would have a set of data, and then we would look at that data. We would decide to fit these different copula structures, and ModelRisk would determine which of these copulas is the best fitting. So in this case, you see the Clayton, which has the best AIC, which is the lowest AIC value. This is the best fitting copula, and that would be the one we would probably use within our model. You'll notice that ModelRisk is capable in this bivariate copula fit, is capable of detecting the direction. So although this is a correlation that's positive, it could also have been that the greatest pinching was in the top right-hand corner, in which case ModelRisk would have identified that even with the same alpha parameter, which is a parameter that defines the level of correlation. It could have determined that this was the greatest, best fit was to pinch more in the top right-hand corner. So let me give you an example model here. The first data set is factors affecting male health. And I'm going to model the correlations between these variables. This is a real data set where I've got a number of variables, age, height, weight, their waist, etc. Measures, cholesterol, body mass index. These are measures that are commonly taken to define how healthy a person is. So let's imagine we wanted to fit a correlation to these values. Well, what we could do is, you'll see here, I've got both copula, multi-normal. In this case, I've used a multivariate normal copula, fitted to these data, and you'll notice that it's linked to the data, and I've got a couple of extra parameters that are not really worth worrying about, but they're about whether the data are in columns or rows, and whether or not we want to include the uncertainty about the fitted parameters, something that we can add into ModelRisk if we want. But for now, I've just got a long array function which reflects the number of variables in my model, and it has internally figured out the level of correlation between each of these variables. I can view function this, and you'll see in the bottom left-hand corner that it has determined a level of correlation between each of these variables. So if I hit the F9 key, which is a spreadsheet recalculate key, you'll see that this line, copula line, is randomly varying, and we're getting values between 0 and 1, the cumulative percentile values that we need. Then what I've done over here is, in this case, just for simplicity, I fitted a log normal distribution to each of these variables independently, and I've not included the uncertainty about parameters, just to make it a simpler model. And then I've incorporated the U parameter. This is another optional parameter. It didn't need to be included, but by incorporating the U parameter from this copula, I am going to correlate each one of these fitted distributions. Then perhaps if you imagine that we have an index, people are supposing we would like to have an index which has this formula, 0.6 times the age plus 0.2 times the weight, blah, 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 blah. And we would like to know that if you take a random individual, what is the distribution that people would have for this particular index? This is a common thing to do in health. Well, those output is reproducing that formula based on each one of these generated values. But they're correlated, remember. So now when I run the simulation, I get a distribution here of this particular index of healthiness. And you can see that, for example, let's pick a tally down here somewhere. You see that anybody who's got a value greater than about 181, according to the index, will be in the top 5th percentile of unhealthiness. So that means you're either very old, or you've got a very big tummy, or you've got a very high pulse rate, etc. So weighting all those different factors, somebody with a score greater than 180, well, they should start thinking a bit more about their health. For the fun of it, I looked at the probability that somebody is greater than 240. So what is the probability of being greater than 240? It's 1 minus rho sim probability on this random variable that they're less than 240, which means that they're greater than 240. 1 minus probability of being less is the probability of being greater. So 2% of people would have an index value greater than 240. Now, what would have happened if I hadn't included correlation in this problem? Well, then I would have had a independence between the age and the height, the weight, etc. That would mean that in this formula here, I could have had one value that was high, but I wouldn't recognize that they tended to occur together, which means I would have got a narrower spread in my distribution for this index. And that would mean that if I would actually look at the index for one individual, they would sit further out in the tail, and we'd be scaring them to death when they actually are not that unusual, because we're not acknowledging the fact that people have correlations between these health indices. Now, copulas assume that when there are several variables, and you saw the Clayton, the Frank, the Gumbel, when there are several variables, we assume the correlation structure between each pair of variables, so if there were 3, there's A, B, B, C, and AC would be 3 pairs, we assume it's the same. Although this normal and student copulas do allow for different levels of correlation, they still assume the same shape, the lozenge kind of shape. So despite the variety of correlation shapes still available in ModelRisk, the copula models don't always fit the data very well. But if the data show that other correlations show some unusual correlation shapes, we can still fit a correlation pattern in ModelRisk using this function that's called the Vos copula data. Some of the benefits of this are that the data copula will absolutely statistically replicate any pattern you have in your data, no matter how few points you have. If you've got one data point, you can say nothing at all about the correlation structure. If you've got 3 or 4, you can say something very vague. Well, the copula data function will progressively, as you acquire more data, start pinpointing more and more precisely what that correlation pattern is. On the other hand, the function is far slower than the other copulas, which means that when the data set's large, you are sacrificing the speed of your simulation for the accuracy. Most times that's not such an important issue. It's much more important to get the correlation pattern right. But it's something to be aware of. So let's have a little look at this data file. Here we have three variables, x, y, and z. And they are correlated in some way. If I was to fit a copula to them, I'm just going to show you what that looks like. Those copula data, and you'll see that it's taking this array of data. It's not fitting one of the Archimedean copulas, that's the Gumbel, Frank, and whatever the other one's called, Clayton. It's not fitting the elliptical copulas, the T or student, and the normal. It's fitting a non-parametric, meaning we do not assume any shape attached to this form. We just want to see if there's a pattern there. So it's picking the data, and the false bit is about whether or not we include the uncertainty. Well, let's have a little look at that function. It covers three cells because there are three variables. Again, it's always an array function. I click on View Function, and you see how interesting. There is a very unusual correlation pattern shown by my data. Let's have a look at the data on its own. There's the data. If we look at the fitted copula on its own, I can change this, make it 5,000 data points. You can see that between variable 1 and variable 2, we have this very strong, rather unusual correlation pattern. Between variable 1 and variable 3, we have kind of the opposite correlation pattern. This is happy, this is sad. And between variable 1 and variable 2 and variable 3, we have very peculiar correlation pattern. Now, this is the fitted copula, this is the data. You can see that we very precisely match in the fitted copula what is being observed in the pattern. In fact, if you look at the data, you'll see the data has a narrower pinch here and here, and the fitted copula doesn't have that same narrow pinch. It's slightly broader. That's because it statistically interprets it, so it's not absolutely sure about the pattern. If we had 1,000 more data points that followed this pattern, then the fitted copula would be tighter and tighter, and more replicate that pattern. But you can imagine if you only got a few data points, you don't want to exactly reproduce the pattern you observed in your data because you're not sure it's real. It's much the same as if you have 5 data points, random samples from a population, you really don't know what the mean is very well yet. In that same way, we don't know what the correlation pattern is very well, and this includes some uncertainty about that correlation pattern. Moving on to a slightly different topic, because I want to cover the various different types of correlation that we occur in real life and that we have to model. I want to look at risk-event correlation. So a risk event is a random variable that may occur or it may not occur. And if it does occur, it has some impact on us. And that could be a positive. Sometimes it's called an opportunity if a risk event has a positive impact. But most often, unfortunately, it's negative. So as in it's bad for us. So it's called a risk event. So a risk event, something like, for example, a fire occurs in a factory. That would be a risk that may or may not occur, and its impact usually follows a distribution. So it has three components: the scenario, the probability of the event occurring, and then the size of the impact should it occur. And there are often correlations between these variables, between different risks. So the idea is that one risk, if it does occur, it can affect the probability of others occurring, or it can affect the size of the impact. You're probably familiar in the news with how BP has just got very strongly penalized and paid the largest fine to the US government of any corporation they ever had to pay. And one of the reasons for the size of that payment could be that just a few years ago they had another accident. And so in that other accident in a refinery, it meant they kind of lost the goodwill of the American people, and so they were hit very hard. You can argue either way, but there are many different situations in which we have correlations between one risk occurring and probability of or the size of another risk that might occur afterwards. So you can produce a chain reaction, and you can imagine that chain reaction, if the probabilities start getting bigger or the impacts start getting larger, if we don't include correlation, we are going to underestimate the tails of our distribution of exposure. It's also important to note that if we incorporate the dependencies, and one of the reasons, of course, we're doing risk analysis modeling is to manage risk. So if we incorporate the dependencies, it does offer us greater opportunity to be more efficient in our risk management. So, for example, a small risk, which has perhaps a small impact, but has maybe a largish probability, we might not really worry about that too much on its own because the impact's small enough. But if that risk does occur, perhaps it strongly increases the probability of another larger risk occurring. And now it becomes quite important to control that small risk. So how do we model correlated risks? Well, Excel offers quite a flexible set of tools for logic, creating logic between variables. And these are very helpful for us in modeling the connections between risks. So, for example, here we've got an if statement and an and an or statement. So we can say if and two risks occur, if risk A is greater than 0, risk B is greater than 0, then the probability is 0.5, otherwise the probability is 0.2. If you model risk events as either zeros or ones in your model, so 1 being the risk occurs, 0 being the risk doesn't occur, we can also produce some very simple logic. So, for example, if sum of these risks is greater than 0, that would mean if at least one of those risks happened when they're all modeled with 0s or 1, if at least one of those happened, then this risk is going to occur, otherwise it doesn't. This one is if the product of these risks is equal to 1, that means they must all be equal to 1. Then this other risk, this last risk, is going to occur, otherwise it's not. There's similar logics and combinations of things that you can easily create. And we can modify either the probability of occurrence or we can modify the impact, and I'm going to go show you an example of that. So here is a project schedule, and we're going to add some risks into this project schedule, into these different tasks on the schedule, on the Gantt chart. And I'm going to do that with this little model here. By the way, at the end of this presentation, for all those of you who subscribe to this webinar, we will send you copies of models that I'm showing to you now, and we'll send you a copy of the slideshow as well, so you can go back over what we've covered. So here's a project schedule model exercise. It's a very simple model. If you've looked in our help file, you will find examples of project schedule models, and this is one of them. So I'm not going to go into the details of how this logic is created to determine the total duration of the project. I'm really interested in this bit down here. This is a table of different risk events. I'll blow it up a little bit so you can see it better. So what I want to be able to show in this model is that if risk 1 occurs, then it increases the probability of risk 2 to 40% from its original value. So here's that logic that describes this. It says if risk 1 is greater than 0, and that's because this is simulating either 0 if the risk doesn't occur, or the size of the impact if it does occur. If I27 is greater than 0, then we write down 40%. We change the probability to 40%, otherwise we leave it at 30%. So you can see if I hit the F9 key, you might have this risk event occurs. You see the probability is 40% now. It doesn't occur, the probability is 30%. So you understand this? Here we've got a Bernoulli distribution representing whether or not the risk occurs or not, a 0 or 1, multiplying it by a triangle just for the impact, 3, 4, 7. The triangle distribution, one can argue about whether that's a good distribution to use, but I use it for illustration here because it's very easy to understand, and it's picking the minimum, most likely, and maximum impact. All right. So when that's 0, it's because the Bernoulli is returned at 0, meaning that the risk event didn't occur. Here we have, if risk 2 occurs, it extends the duration of risk 3 by 2/8. So here I've got a formula to describe that. This is first part here is just simply modeling the original risk, and then add to that, if I28 is greater than 0, so that means the risk 2 occurred, then we put a value of 2 in, otherwise 0, and we're adding that onto the total duration. Notice that we've got brackets around here because this only applies if this risk event actually occurs in the first place. So we've got a Bernoulli distribution, which is either 0 or 1, multiplied by this triangle plus potentially the impact, extra impact of 2 weeks if risk 2 does occur. And the same, we've got similar logic here for risk 3, but it affects both the probability and affects the impact. I don't think I need to carry that. You can look at it in the model in your own time. Finally, I want to spend a few minutes just talking about time series correlation. So we've covered correlation when you've got dichotomous variables, the 0, 1s or yes, no's. We've covered correlation between probability distributions. We looked at correlation between risk events. And now, lastly, we want to look at correlations within time series. So within a time series, you can have a random variable that may take a range of values. And perhaps we have correlations from one value to the next through time. So here is an example of that. We've got a subject matter expert 3-point time series. So the idea of this is the red line represents the maximum this variable can take over time. The blue line is the minimum. And the green line you may just be able to make out is your best guess. And in this case, it's fitting a triangular distribution around these 3 points. But it's trying to say that they're correlated. Now, if this was something like the number of sales you might make for a new product, you can imagine that if your product does well, then it's going to make towards the upper end of these 3-point distributions, defined by these 3 blue, green, and red dots. So this pathway is going to pick a high value to start with, and then it's going to pick a relatively high value as well for the second period, and for the third period here, and for the fourth and fifth. And the way this is done in ModelRisk is using, when we use this time series, 3-point time series function, you use a correlation here of 0.9. So let me show you an example of that. Here I have a minimum, a most likely, or mode, and a maximum, 3-point estimates going forward from periods 2013 to 2019. I've got a correlation of 0.8, and here I've got those time SME 3 points. So this is a 3-point time series, the one I just showed you in the previous slide. A view function, you will see the minimum values, the most likely values, and the maximum values. And you'll see a correlation of 0.8. What does that mean? Well, if I change the number of lines here from 1, you're seeing one potential pathway to, say, 10. You can see, when I highlight one of these, that this pathway is always staying at a low value. This one pathway here it's moving around a little bit, but it's kind of on the low side. This one, it's staying in the high side, etc. If I change the correlation to, say, 0.9999, that's an extremely high level of correlation, and then you can see the effect. A very high level of correlation, you're going to have essentially the same percentile occur from each of these triangular distributions at the same time. And if I have a 0 correlation, you can see what that looks like. Any one of these samples is randomly moving between potentially a minimum and maximum of each of the variables. They're going to have more samples taken in the middle, not because of any correlation, but because we're defining this as a triangular distribution, and of course that means that for the mode, there are more values going to be picked around the mode. So you'll see more samples are passing somewhere near the mode than towards the tails. Okay, so in the SME time series, the subject matter expert time series, we can incorporate correlation. We can also incorporate correlation across time series. In the financial time series functions we have within ModelRisk. These are generally used for modeling things like interest rates, exchange rates, stock prices, the prices of commodities, where we know that they tend to go up or down in time. Well, we're not really interested about the individual values of each of these variables, whether 300 or 90 or 210. It's not the values themselves that we're correlated. What we tend to correlate is the movements as a percentage of itself. So it's very similar, but it's actually called the log return. The log return is a measure of how relatively large the increase of one variable is. And when we talk about relatively large, it allows us to essentially work in the same scale. So three variables here, the three series, that you can see that they've gone up together. You can see this peak here. There's a trough, and then a peak, and another trough. All of these variables are exhibiting the same kind of behavior, even if their values are quite different. Well, they're determined, this is always determined by fitting, and it's part of a covariance matrix. So when you fit, for example, a multivariate time series, in this case it's multivariate geometric Brownian motion, then in ModelRisk, when you export the results to the spreadsheet, the fit, you can see a pattern, a correlation matrix being created here. This is, in fact, a combination of correlation and variance. So this is a covariance matrix, but the correlation is embedded inside this little table because there are three variables. It's a 3x3 matrix. Just to remind you that if you want to read any more about these topics, then we'll be sending you the PowerPoint slide, and you can just type M083, for example, into your Excel. So the help file, if I type in search M0803, enter, and you'll see that the only topic that will pick up is log return of a time series, and then you can read about what on earth that time series log return really meant. So this is the end of my presentation. I hope you've enjoyed yourself. Just to reiterate, we will send you by email, for all of those registered on this webinar, a copy of the models that have been demonstrated to you in this presentation, a copy of the PowerPoint slideshow so that you can go back over it in your own time. This webinar gets recorded, so we will have on our website the ability to click and listen to my voice again in a streaming version. If you do have any questions, please send me an email. This is my email address, david@bosoftware.com. You can telephone our office there, +32 932 40623. And you can visit our website, bosoftware.com, where you will find other webinars that have been done over the last couple of months. There are a lot of other training videos that you can also look at. And there are also training courses that you can purchase from us from our website. So I like to think there is a great wealth of information that will help you create really good risk analysis models. So as a final comment, we spend a lot of effort considering the different types of probability distributions that we will use within a risk analysis model, and we spend very little effort thinking about correlation. So I urge you to change that way of thinking, to consider that not including correlation is more of a statement than including correlation. To not include correlation is really, you should be saying to yourself, I'm quite convinced there are no relationships between these variables. If you're not convinced about it, then you don't really have much of an excuse for not including correlation in some way. So thank you very much for your time. I hope you've enjoyed this webinar, and I will finish now.